All right, hi everyone, and welcome to my double lecture on least squares and inner products. So, um, today we're going to be talking about two topics. One from, I believe, 15.3 and one from 5.3 and one from 5.4. So, both of these topics are kind of very, very tied together, and I kind of want to illustrate why that is, but I'll kind of get to that towards the end. So I'm going to start with the least squares problem, which is among the most famous in mathematics. So here it is. So given an m by n matrix A, so we can think of A as a linear transformation from Rn to Rm. I want to consider the following problem. For a fixed vector v, consider the problem of minimizing the length of the vector ax minus b by varying x in Rn. So of course the length of ax minus b is simply going to be the scalar product of this vector with itself. So this is the same thing as ax minus b transpose times ax minus b. And here is a somewhat obvious remark. If the system ax equals b is solvable, then this minimum is 0. Well, why? I mean, the length, of course, is always greater than or equal to 0. And if we can solve this system, then we can find a vector here, ax minus b, that is simply the 0 vector, so it has length equal to 0. So this is the least squares problem. And it is among the most important problems in mathematics. So let me try to illustrate why. So here will be example 1. Given a collection of inputs xi, and these are going to be real numbers, and outputs yi, then the problem of finding the line y equals ax plus b, best fitting the data, is a least squares problem. So this is one such example. In fact, this goes under a name that you may or may not have heard before. This is the problem of linear regression. Here is another example. Given a plane in R3, and I'll call my plane S, and a vector V in R3, finding the vector closest to V in S is also a least squares problem. So if you note, the first example we gave right here is a problem of statistics, whereas the second problem we give right here is a problem of geometry. And yet somehow these are both examples of the same kind of problem that we've described here. And we'll see why that is later today. But the general motivation is as follows. So if we cannot solve ax equals b, then we can try to get ax as close to b as possible. So in many ways, least squared problems are kind of problems of saying, okay, we have a linear system. We can't solve it, but maybe we can get it really, really close, or at least as close as is possible. So as you might guess, this is kind of a reoccurring motive in mathematics. Anytime you have a linear system that you can't quite solve, you can try to solve it solve it approximately in the best way possible. And so this is really the heart of it, and this is why least squares type problems appear over and over again in mathematics. So I'm going to start by kind of proving a lemma. The book calls it a theorem that will be used in our kind of general approach to solving least square problems. So here it is. Suppose we have a subspace of Rm. Then for each b in Rm, there is a unique element p of S that is closest to b. That is, b minus y is greater than b minus p for any y not equal to p in S. Furthermore, a given vector p in S will be the closest to a given vector b in Rm if and only if b minus p is in the complement of S. Okay, So here's how we're going to approach this. We're going to use the following fact that Rm has a direct sum decomposition. So let me just say this is going to be our proof. And this direct sum decomposition is the direct sum of S plus S transpose. Thus, B may be written uniquely as P plus Z, where P is in S and Z is in S, or the orthogonal complement of S. Okay. Now, what we can do is we can look at the length of B minus Y. Well, this is the same thing as B minus P plus P minus Y. All I'm doing is I'm putting in a negative Y and a positive Y to cancel each other out. And we can gather terms. This is the same thing as B minus P plus P minus Y. Now there's a reason we're doing this. The reason we're doing this is we know that B minus P is equal to Z, which lies in the orthogonal complement of S, and both P and Y live in S. So if you take their difference, P minus Y also lives in S, which means these two vectors are orthogonal. So what I'm going to do here is I'm going to go through and I'm going to square each of these. So all these equalities are still true for the squares. But now observe that this last thing right here is the same thing as the scalar product, which I'll write like this, of B minus P plus P minus Y, B minus P plus P minus Y, and this in turn is the same thing as B minus P, the scalar product of it with itself, plus 2, the scalar product of B minus P with P minus Y, plus the scalar product of P minus Y with P minus Y. Now, because this vector and this vector are orthogonal, this quantity right here is equal to 0. So this, in fact, is the same thing as the length of B minus P squared plus the length of P minus Y squared. So we can take everything we have to a new page. And it tells us that B minus Y squared is going to be equal to B minus P, or the length of B minus P squared, plus the length of P minus Y squared. And this shows, since both of these terms right here are positive, that the length of B minus Y is always greater than or equal to to the length of B minus P. So P is the vector in S that is closest to B. Also, if y is not equal to P, the above inequality is strict. So, later, and this is going to be in just a little bit, today, we will understand P as the orthogonal projection of B onto S. So, this shows a couple things, if we think about it. It shows that the element in S that is closest to B is precisely the term P that appears in the direct sum decomposition of B according to these two subspaces. And so this is going to be kind of one of the lemmas we use to understand what's going on. Now, let's move on to the more general problem. So, now, what we're going to do is we're going to let A, B, and M by N, actually I'm going to do an N by M matrix. So let A be an N by M matrix. And we're going to assume A has rank M. And we're going to consider the problem of minimizing the square of the norm of AX minus B for some fixed B in Rn. Okay, so here's the key observation we're going to use. We are trying to find the vector P in the column space Ra of A closest to B. Now, this is very helpful because we know a very useful fact. This is a very, very useful fact. And the useful fact to us is that the orthogonal complement of the column space is in fact simply the null space of A transpose. So, this leads us to the following observation. What we can try to do is we can try to write, or we can try to observe that if P is the vector in the column space, closest to B, then we can look at the square, the norm squared, of AX minus P plus plus B minus P. And here's the key observation. So this right here lies in the column space of A. And this right here lies in the null space of A. Consequently, or actually, hold on one second. I'm going to do this slightly differently. A somewhat easier way to say this. Let's just take the identity we have. This one right here. If AX is the vector in our A closest to B, then AX minus B actually has to live inside the orthogonal complement of the column space. Consequently, it has to live in the null space of A transpose, which means A transpose times A X minus A transpose times B has to be equal to 0, which is the same thing as A transpose A is equal to, or times X is equal to A transpose B. And so now we can ask the following question. When can we solve this equation? And so this leads to the following theorem. If A is an m by n matrix, then the normal equations A transpose times A times X equal to A transpose times B has a unique solution. if the matrix has rank n. And this unique solution is in fact the least squares solution of Ax equals b. So what we need to show is that if A has rank n, then A transpose A is invertible. So here's how we're going to show this. Suppose that A transpose A times Z is equal to 0. Then, well, A transpose Z, or A times Z, lives inside the null space of A transpose, but it also lives inside the column space of A. And the reason the first equation is true is simply because we have A transpose applied to AZ is equal to 0. And so that is equivalent to that. But now if both of these statements are true, then we can use the fact that RA is the orthogonal complement, or I'm sorry, the null space of A transpose is the orthogonal complement of the column space. So here's what that means in practice. AZ lives in the column space of A, but it also lives in the orthogonal complement. And if something lives in a subspace and its orthogonal complement, it implies that AZ is equal to 0. So if A transpose times AZ is equal to 0, then it follows that A times Z is equal to 0. But since A has rank n, and it has n columns, the columns are linearly independent. Which implies that Z actually has to be equal to 0. And now this gives us the necessary condition we need to solve our last equation. Because we were seeking x that minimized the equation ax minus b squared. And we showed that if such x minimized this equation, then we had to have that ax, or I'll actually spell it out. If x minimizes the equation, then ax minus b has to live in the null space of A transpose. But that in turn implies that A transpose AX is equal to A transpose B. Now, the next implication follows from the previous theorem, because if A, or I'll say it like this just to be completely concrete. If the columns of A are linearly independent, then we have to have that AT times A is invertible. Which in turn implies that X is equal to the inverse of A transpose times A multiplied by A transpose times B. And this is the solution of the least squares system. And this is also, in turn, the basis for a very, very, very large chunk of statistics. So now we're going to do some examples that kind of show exactly how powerful this is. So here's our first example. And also at this point, I'm going to start using matrix equation solvers to kind of speed up the process a little bit. So I found a good one earlier. Let me find it again. So let's see. I don't like those. What was the one I was using? Hold on. All right, maybe I'll just use Wolfram. So I'm going to use this right here. And here's our first problem. What we want to do is we want to find the least square solution of the following system. So I'm going to have 1, 1 here, negative 2, 3 here, and 2, negative 1 here. And I'm multiplying this by a vector, x1, x2. And I'm setting this equal to, let's see, 3, 1, 2. All right, so we can take for granted that this equation is probably not going to be solvable. But we can still try to find the best almost solution, the least square solution. So in order to do that, what I have to do is I have to compute the following quantity. Well, first I write down my A transpose. A transpose here is going to be 1, 1, negative 2, 3, 2, negative 1. And then I take my vector right here, and I compute A transpose times B. This is the same thing as 1, 1, negative 2, 3, 2, negative 1, multiplied by 3, 1, 2. So if I do that, let's see what I get. I'm going to get a vector with 2 rows. And this will precisely be 5 in the first entry. And then in the second entry, I'm going to have 4. So the next thing I have to do is I have to compute A transpose times A. So in this case, what I want to do is I want to compute this, and this will simply be 1, -2, 2, 1, 3, -1, multiplied with 1, 1, -2, 3, 2, -1. And if I compute this, I'm going to get a 2 by 2 matrix. So let's see what my first entry here is. I believe it's 9 here. My second entry is going to be, so 1 times 1, -6, -2. So I believe this is -7. And then the next one is going to be this column times this row. So 1, -6, -2. So that's also going to be -7. And then finally, I take this column and this row, and I get, I believe, 11. So let me double check myself. And that's correct. So the system I actually need to solve at this point, the least square system, is 9, -7, -7, 11 times x1, x2 is equal to 5, 4. So at this point, you could solve this linear system using any of the techniques in this class, but just to be lazy, I'm going to solve it using Wolfram Alpha at this point. So I have two equations. My first equation is 9x minus 7y is equal to 5. My second equation is negative 7x plus 11y is equal to 4. So if I solve this, I get an x and a y. In this case, an x1 and an x2. So 83 over 50 and 71 over 50. So this is our first example of a least squares type problem. So let's do another example. So consider the subspace of R3 spanned by the vectors one, 1, 1, and 1, 0, 2. Find the vector P in the subspace closest to 1, 2, 3. So this is actually very similar to the problems that we were talking about when we started talking about orthogonality, when we're trying to find the distance from a point to the plane. Here, rather than find the distance from a point to the plane, what we're trying to do is we're trying to find the vector in the plane that is closest to a given vector. But if you find it and you subtract it from this and you take their distance, then you get exactly the distance of a given vector from the plane. So here's how we can do this. We can recognize, first off, that the span of 1, 1, 1, 1, 0, 2 is the same thing as the column space of A, where A is the matrix. First column 1, 1, 1, second column 1, 0, 2. So finding P essentially amounts to solving the least square problem. AX equals 1, 2, 3. And computing AX. So let's see how this goes. Well, first thing we're going to do is we're going to take our matrix. I'm going to compute all the relevant quantities to us. So first thing we're going to do is we're going to note here that A transpose is simply the matrix 1, 1, 1, 1, 0, 2. So A transpose times A is the product of these two matrices. And we can compute it pretty easily. And it will just be, we're going to get a 3 here. And then we're going to get a, let's see, a 3 here, a 3 here, and then finally a 5 here. And we also have to compute A transpose times B, which in this case is 1, 1, 1, 1, 0, 2, and then multiplied by 1, 2, 3. So this is just going to be the vector. Let's see. 6 in the first entry, and then 7 in the second. And so now what we want to do is we want to consider the system A transpose A times X is equal to A transpose B. And I should note that when I'm solving these systems, I'm implicitly using the fact that the columns of A are linearly independent. I did this on the preceding example as well, even though I didn't spell it out concretely. So because the columns of A are linearly independent, we can actually solve this system. And the system is the same thing as 3, 3, 3, 5 times x1, x2 is equal to 6, 7. And now we can solve for x1 and x2. Again, at this point in the course, we've solved enough linear systems, so I'm just going to go to Wolfram Alpha to help us out. And here we're going to find 3x plus 3y is equal to 6. And then 3x plus 5y is equal to 7. And if we solve this, we get x is 3 over 2, and we get, or x1 is 3 over 2, and x2 is 1/2. So what we've accomplished is we've solved the system, but we still need to find the vector p. So the vector p here is simply going to be a times 3 over 2 and 1/2. And so this is going to be 1, 1, 1, 1, 0, 2, multiplied by the vector 3 over 2, 1/2, which is going to give us, let's see, in the first entry we're going to get 2. In the second entry we're going to get 3 over 2. And then in the third entry we're going to get 3 over 2 plus 1, so 5 over 2. And so this vector right here is the vector closest to 1, 2, 3 in the column space. All right, so let's do another example. How do I? Okay, good. All right, so for our next example, we're going to consider the problem of interpolation. Or, well, actually, in this case, it's just going to be linear regression. So example 3. Suppose an experiment is run three times. With one dependent, or actually I'm going to use simpler language, with one input variable, xi, and one output variable, yi. The researchers believe there is roughly a linear relationship between the yi and the xi. Find the line best approximating it. Or I maybe say best approximating the following data. So say we have the following table. So we have xi and yi, and we have I equals 1, I equals 2, I equals 3. So for 1, we're going to get the input was 5. For 2, the input was 6, and for 3, the input was 7. And then for I equals 1, we get 11. And then for 6, we're going to get 13. And then for 7, we got 17. And so what we're trying to do is we're trying to find A and B with y equals ax plus b, best fitting the data. So I'm going to use this example to illustrate a general method. What we're trying to do is we're trying to, in some sense, choose A and B such that A times x, or actually, how about I spell it out in every detail? We're trying to choose A and B such that A times 5 plus B is close to 11, and A times 6 plus B is close to 13, and A times 7 plus B is close to 17. And what we want is we want A and B to kind of, actually not kind of, exactly, to minimize the distance between the vectors A5 plus B, A6 plus B, A7 plus B, and 11, 13, 17. So, as you probably might suspect, this is exactly a least squares problem, and we can understand it as such. So framing it in least squares, what we're trying to do is we're trying to find A and B such that if we multiply it by the following matrix, so here we're going to have 5, 6, 7, corresponding to the input variables, and here we're going to have 1, 1, 1, corresponding to the constant terms. We're trying to make it so that this matrix product is closest to 11, 13, 17. And so now we've reinterpreted the statistical problem in terms of a least squares problem. So this is my A, this is my X. You know what, I'm going to call this C, rather. Actually, I'm going to call this, give it a different letter just to be safe. I'm going to call it Y, because I don't want to use little a or little b. So this is our least squares problem. We want to make AX here as close to Y as possible. So in order to go about doing that, what we need to do is we need to compute various quantities. So first things first, let's write down A transpose. So this right here will be 5, 6, 7, and then 1, 1, 1. And then we also need to compute A transpose times A. So this is going to be the matrix product of 5, 6, 7, 1, 1, 1, and 5, 6, 7, 1, 1, 1. And so this will be, let's see, we're going to have 25 plus 36 plus 49. And so this is going to be the same thing as, let's see, this right here is, I believe, 61. 61 plus 49 is equal to 101. So we're going to get 101 here. And then we're going to get 5 plus 6 plus 7. So in that case, that's 18 here. We're going to get 18 here as well. And then we're going to get 3 here. So this computes the computation of A transpose times A. I also have to compute the product of A transpose with Y, which in this case is 5, 6, 7, 1, 1, 1, multiplied by the vector 11, 13, 17. So let's try to figure out what this is. For this, I will actually use Wolfram Alpha to help me with the arithmetic. So I'm going to do 11 times 5 plus 13 times 6 plus 7 times 17. I'm missing an addition sign right here. $252. So I get 252 here for my first entry. And then for my second entry, I just get the sum of 11 plus 13 plus 17, so 41. All right. So now I have all the data I need to set up the linear equation that I need to solve. So I need to look at 1, 0, 1, 18, 18, 3 times AB is equal to 252, 41. So to solve this, I'm going to go into Wolfram Alpha and use the linear equation solver. So I have to solve 101 A plus 18 B is equal to 252. Which maybe I'll stick with the letters that they use. And then I also have to solve 18A plus 3B is equal to 41. Oops, I'm being an idiot. So this gives us let's see. A here is going to be equal to -6 and then over 7. And B here is going to be equal to 395 over 21. Let me just verify that I did this correctly. Sanity check myself. And so this gives me my A and my B. So with that in mind, I can do, well, the problem is done. So let's do one more least squares type problem. So this will be my fourth example. And this is going to be kind of a upgrade of the previous problem. So suppose researchers have a collection of trial results with dependent variable xi and outcome variable yi. They believe xi and yi are related by a quadratic function. ax plus, or ax squared plus bx plus c. Given the data, find the quadratic function best approximating it. So here's what we have. We have a table of xi and yi's. And as before, we're going to have three different things: I equals 1, I equals 2, and I equals 3. And so when we put 2 in, we're going to get 5. When we put 1 in, we're going to get 3. And when we put negative 1 in, we're going to get 6. So what we want to do is we want to find the quadratic function best approximating this data. So this is the same thing as considering the following linear system. A times 2 squared plus b times 2 plus c, let me clear that that's a 2, is equal to 5. And then a times 1 squared plus b times, actually, hold on. I'm going to add an extra trial result here, so I'm going to add I equals 4. And this is going to be 0, 1. And so then b times 1 plus c is equal to 3. And then I also have that a times negative 1 squared plus b times negative 1 plus c is equal to 6. And then finally, I have C is equal to 1 because I have A times 0 squared plus B times 0. So I have this linear system. And what I want to do is I want to find the A and the B and the C that make the left side of this as close as possible to the right side. And so this, again, is a least squares problem. So let's see how this goes. What we do is we simply convert it into a matrix form. So I'm going to have my A, my B, and my C here. And then it's going to get multiplied by a 4 by 3 matrix. So here I'm going to have 2 corresponding to the square term here, a 2 corresponding to the linear, a 4 corresponding to the square term, a 2 corresponding to the linear term, and a 1 corresponding to the constant term. Likewise, I'll have 1, 1, 1 here, and then 1, negative 1, 1 here, and then 0, 0, 1. And I want this to be equal to 5, 3, 6, 1. So, this is my least squares problem. So let's give names to these things. I'm going to call this matrix here A. I'm going to call this vector here X. And I'm considering the equation AX equals Y. So in order to solve this, what I have to do is basically sit here and compute all the relevant data. So the first thing I'm going to note is that A transpose is equal to the matrix 4, 1, 1, 0, 2, 1, negative 1, 0, 1, 1, 1. Now I have to compute A transpose A. And so this is going to be the same thing as this multiplied with this. So let me grab it. Okay, I hate that. I'm just going to rewrite it. This multiplied with this. Let me shift it over a little bit. And now let me compute their product. And their product will, of course, be a 3 by 3 matrix. So if I multiply this by this, first column by first row, I get 16 plus 2, so I get 18. And then if I multiply this by this, I'm going to get 8. And if I multiply this by this, I'm going to get 6. Now if I multiply this by this, I'm also going to get 8. If I multiply this by this, I also get 6. Now if I multiply this by this, I simply get 2. Same thing if I multiply this by this. And then if I multiply this by this, I believe I get 6. And if I multiply this by this, I get 4. So this gives me A transpose times A. So now that I have A transpose times A, the other thing that I need to get is I need to get A transpose times Y. So I'm going to go over here and I'm going to take my A transpose and I'm going to move it over here. And I'm going to consider the following equation, which is A transpose times the vector 5, 3, 6, 1. So let's see what I get. This is going to be a vector with 3 components. I'm going to get 20 plus 3 plus 9, so 29 for my first component. And then for my second component, I'm going to get 10 plus 3 minus 6, so 7. And then for my final component, I'm going to get 5 plus 6 plus 3 plus 4, 1. So I believe that's 15. Let me double check. Yeah. And so this gives me A transpose times Y. And now I can actually write down the linear system of interest to me. So I'm going to go to a new slide. And what I want to solve is I want to solve this linear system. So 29, 7, and 15. And again, I could solve this by innumerable techniques, but because we've solved enough linear systems at this point in this course, I'm going to use a calculator. So if I use a calculator, first I'm going to have 18x plus 8y plus 6z is equal to 29. And then I'm going to have 8x plus 6y plus 2. Is that a 2? Okay, plus 2z is equal to 7. And then I'm going to have 6x plus 2y plus 4z is equal to 15. So after inputting all of these, I can run through the calculation. And what I find is I find that A is equal to 7 over 4. I find that B is equal to negative 37 over 20. And I find that C is equal to 41 over 20. And this gives me the quadratic equation that best fits the data. So let me wrap up what I have to say on least squares by casting this in an appropriate generality. So here's how this goes. Given training data, xi and yi, in machine learning these are called samples. We can use least squares to perform a regression best fitting a polynomial an xn plus an minus 1 xn minus 1 plus blah, 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 A0 on to the data. Xi, yi by applying least squares to the matrix. Or the matrix equation. Xi, or x1 to the n, x1 to the n minus 1, and then blah, 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 x1, and then 1, x2 to the n, blah, 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 xm to the n, blah, 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 xm, 1. So we get this big matrix that we build basically by using our input variables xi, our independent variables, and we kind of make the first column here be the nth powers, the second column the n minus 1 powers, blah, 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 and finally in the final column we just have our constant terms. And then what we're doing is we're multiplying this by an minus 1, blah, 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 a0, and we're setting this matrix equation equal to y1, y2, all the way through ym. So not only does this cover the notion of linear regression that you would learn in statistics, or least squares linear regression, it also covers the notion of fitting a given set of data with a polynomial of an arbitrary degree. So, this is the power of the least squares method. And in some sense, all of statistics is based around it. So now we're going to move on to another topic. And the next topic is going to be inner product spaces. And so this is going to allow us to generalize a lot of the work we've done so far. So, given a vector space V, an inner product on V is an operation that assigns a number to any two vectors v and w in V, and satisfying the following properties. So the first property is that if we take the inner product of a vector with itself, we're going to get a number greater than or equal to 0, and the inner product of a vector with itself is equal to 0 if and only if x itself is equal to 0. The second property is what we call symmetry. So it means that if we reverse the order of the arguments, we get the same thing. And the final property is what's called bilinearity. And so bilinearity here means that alpha x plus beta y, if I take the inner product of this with z, it's the same thing as alpha times the inner product of x with y plus beta times the inner product of y with z. And I'm sorry, I botched this slightly. This right here should be z. So these are the three properties describing an inner product. Now, just give me 1 sec. I'm going to go grab a glass of water. All right, I'm back. So the reason we're defining inner products is, in fact, we want to generalize the one we've already learned. And so this will be our first example. And so for this example, what we're going to do is we're going to note that if x and y are in Rn, then the assignment, actually I'll call it by the name I introduced it as, then the scalar product assignment this is x transpose times y, is an inner product. And in fact, we've verified all the properties of an inner product already. So there's not much else to say. The best way to think of an inner product is to understand inner products as things that generalize the scalar product. For the last 3 classes, we've been using the scalar product, and we've used it to define notions of orthogonal spaces. But in fact, anytime you have a more general inner product on an arbitrary vector space, you can do very similar such things. So the goal of this chapter is to kind of show some other inner products and then show how techniques that we've developed for the scalar product also apply to these other inner products. So here is one such example. So example 2. So what we're going to do is we're going to consider R m times n. So this is the space of m by n matrices A. And I'm going to denote it by having components aij. Then Rmn has an inner product AB given by computing the sum from I equals 1 to m of the sum from j equals 1 to n of aij times bij. Yeah. In fact, by identifying Rm times n with Rmn, this is just the standard inner product, or the scalar product. So there's nothing really new in this example, but it does show that, we can define inner products not just for Rn, but also for spaces of matrices, even though secretly this is also the case in Rn. The next example is more interesting. So this is going to be example 3. I want to recall that CAB is the vector space of continuous functions on the closed interval a to b. So we can actually give this vector space, which, as we've talked about before, is infinite dimensional, an inner product structure. So CAB has an inner product So what I'm going to do is I'm going to take two functions, f and g, that are continuous on the closed interval, and I'm going to define their inner product as the integral from a to b of f of x times g of x dx. And so now what we're going to do is we're going to verify that this is an inner product. So this is to say we have to verify that all three of these relations holds. Okay. So the first thing we're going to do is we're going to look at the inner product of f of x with itself. And so this right here is the same thing as the integral from a to b of f of x squared dx Now, if f of x is not 0 at some point, x naught, then there is a subinterval c to d containing x naught where f of x is non-vanishing and the absolute value of f of x is greater than or equal to little m for some m. So, in such a situation, we have that the inner product of f of x with itself, or I'm calling this an inner product, but I haven't verified that it is an inner product yet, is equal to the integral from a to b of f of x squared dx, which is greater than or equal to the integral from c to d of f of x squared dx. But on this smaller interval, we know that the absolute value of f is greater than or equal to m, so this has to be greater than or equal to m squared times d minus c, which is greater than 0. So, consequently, if this quantity right here is equal to 0, then this implies, in fact, that f of x has to be equal to 0 for all x in the closed interval a to b. And you can also see right away that because you're integrating a positive thing, namely the square of a number from a to b, we in fact always have that this is greater than or equal to 0. So this completes our verification of the first property of an inner product. The second property of an inner product is easier than this, because we can look at this. Well, this is defined to be the integral from a to b of f of x gx dx, which, because multiplication of functions is commutative, is the same thing as the integral from a to b of g of x of f of x dx, which of course is simply equal to g of x f of x. And so this verifies that this construction we've made is symmetric. And then the final verification, what we have to do here is we have to look at alpha f of x plus beta g of x, and now I'm taking the quote-unquote inner product of this with h of x, and so this should be the same thing as the integral from a to b of alpha fx plus beta gx, all multiplied by hx dx. But now I can just use the fact that the integral is linear to see that this is the same thing as alpha times the integral from a to b of f of x hx dx plus beta integral from a to b gx hx dx, which of course is the same thing as alpha times this plus beta times this. And so this shows that this construction right here actually forms an inner product on the set of continuous functions. So I'm going to do one last example. So example 4, let x0, x1, xn be n plus 1 distinct numbers. And then what we're going to do is we're going to set Pn to be the vector space of polynomials of degree less than n. Then what we can do is we can define an inner product on this vector space. So given a polynomial px and qx, in Pn, we can use our n plus 1 points. Or I'm sorry, I should index these from 1 to n, not 0 to n. Then we can use these n points to define an inner product on this vector space. And the way this inner product is defined is that it's defined to be the sum of the products from I equals 1 to n of p xi times q xi. And so the claim, which I will not verify, is that Pn, or I should say, this assignment is an inner product. Okay. So now that we've got those notions out of the way, we can introduce a few other things. But the first thing I want to prove is I want to prove the Pythagorean law. Because every inner product space has a Pythagorean law. So suppose V is an inner product space, which is to say it's a vector space with an inner product. If little v and u are elements of V, we say V and U are orthogonal if the inner product of V and U is equal to 0. And this is a direct generalization of our notion for orthogonality in dimensions 2 or 3 with the standard inner product. And so here is our first theorem. And this is the Pythagorean law. So here's what the Pythagorean law tells us. If V, actually, I need to say one more thing real quick. That I almost forgot. So if V is an inner product space, we have a notion of orthogonality. We also say that the length, or in fact, we're going to start using the adult term, norm, of V is the square root of the inner product with V, and we denote it by 2 bars around V. And I guess I shouldn't say we also say, I should say we define. So this gives us 2 generalizations of notions we've already seen. It gives us a generalization of the notion of orthogonal vectors to an arbitrary inner product space. And it also gives us the notion of length. So these are notions that we had in R2 and R3, but now we can have them in any vector space that has an inner product. So now we can use the first theorem that connects them, or prove the first theorem that connects them. And so this is the Pythagorean law. And so the Pythagorean law states that if U and V are orthogonal vectors, then the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. The proof of this is very easy. So here's how the proof goes. The norm of u plus v squared is the same thing as the inner product of u plus v with u plus v, which is, of course, the same thing as u times the inner product, or actually, how about this? Which, of course, is the same thing as u inner product with u plus v plus v inner product with u plus v. But this, the term on the left here is the same as, by symmetry, the inner product of u plus v with u. And the term on the right here is the same thing, of course, as the inner product of u plus v with v. But these, of course, are the same thing as the inner product of u with u plus the inner product of v with u. And then over here, this is the inner product of u with v plus the inner product of v with v. Now, by symmetry, I have that the inner product of v with u is equal to the inner product of u with v. But either way, it doesn't matter because I've assumed that they're orthogonal. So in both cases, these are equal to 0. So in fact, this is the same thing as the inner product of u with u plus the inner product of v with v, which is the same thing as the norm of u squared plus the norm of v squared. So this is our Pythagorean law. Now, let's do one example to finish up for today. So here's what I want to observe. We're going to look at the vector space C. This is going to be functions from negative pi to pi. And I'm going to look at two functions in here. So my first function, f of x, is going to be sine of x. My second function, g of x, is going to be cosine of x. And the first thing I'm going to do is I'm going to look at the inner product of these two things. So if I look at the inner product of f and g, this is the same thing as the integral from negative pi to pi of sine of x times cosine of x dx, which is, of course, the same thing as the evaluation of 1/2 and then sine squared of x evaluated at pi and negative pi. But this, of course, is simply 0. So, with respect to the inner product, f and G are orthogonal, we can also observe that if we integrate, or if we compute the inner product of f with itself, and this is the same thing as the integral from negative pi to pi of sine of x squared, which you can verify just by, say, using the half angle formula from trigonometry. You can verify that this integral right here is in fact simply equal to pi. Likewise, you can compute the inner product of G with itself. And this is going to be the integral from negative pi to pi of cosine squared of x dx. And again, you can verify that this is simply pi. So, suppose we want to compute the length of 5, or the norm of 5 times sine of x plus 6 times cosine of x. Well, since we know that f and g are orthogonal, the Pythagorean law in fact tells us that this norm is the same thing, or the square of this norm is the same thing as 5, or the norm of 5 sine of x squared plus the norm of 6 cosine of x squared. And this is just the same thing as 25 pi squared. Actually, no, I'm sorry. Just 25 pi, and then plus 36 pi. It's equal to 61 pi. So this enables us to easily compute the norm of the sum of two orthogonal things, because the Pythagorean law tells us that the norm squared splits into two parts, well, the two orthogonal parts. So this is one way in which the notion of orthogonality generalizes to a context where it's somewhat surprising that there even is such a notion. Anyways, that is all I have for this double lecture. We will have our exam tomorrow, or Friday, and we'll have our review session tomorrow night. Our review session will be at 8 p.m., and then on Monday we're going to pick up again with orthogonality and look at some more examples and kind of see how inner products allow us to generalize a lot of the work we've done so far.